Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back. Students, finally we reached to our desired lecture, in which we will discuss the needed steps followed in the design of a single reinforced concrete beam. So, as in lecture 01 part 12, I think so, we discussed the required steps for the review of any beam section or any concrete section. So those steps were discussed in lecture 01 part 11 or 12, I think so. So where we can see the required steps, how to start a review problem and what we need in the review or analysis of a section. In this lecture we will discuss the required steps which will be followed in the design of a singly reinforced beam section. So let's start. First of all, we have data, right? What type of data we need? We need bending moment or load and span of the beam, right? This is our requirement. We need bending moment or we need loads, and the span of the beam, because if you want to calculate bending moment or load, we need span as well of the beam. So this is one type of data which we need. Second type of data which we need, the material strengths, that is Fc prime, Fy, and modulus of elasticity of steel. And the third one is the required architectural depth, because we know almost all the time a drawing comes to the structure section, structure design section, from architectural section or architectural division, because an architect design any architecture of any building, and then they transfer that plan to the structure engineer, and structure engineer then start the structure design of that section of that plan. So there is some kind of beam widths and depths mentioned by the architect. So if any depths are mentioned, so we need that depth, what depth an architect needs. The second step is we need required, which we have to determine. What we need to determine, we need the dimensions of the section, which we will find out. We will find out B and D of the section. A is steel, that is area of steel. We will calculate this. And detailing, which is the most important step of structure designing, right? And finally we need bar bending schedule. This is the work of a structural engineer. He may be responsible for to find out the B and D of the section, area of steel, and detailing and bar bending schedule. So any beam can be designed by two methods. Right? We have two methods. The one method is selecting the trial dimensions of the beam, right? This method is usually used, trial dimensions. That is, we assume B and D by using some kind of thumb rules. Second method is by selecting or choosing the steel ratio. Steel ratio, that is rho, and we always select row less than or equal to row max. So we will assume any initial value of the row, and on the basis of this we calculate area of steel, dimension of the section. So this is a way of designing. I have already recorded lecture on this method. I will share the link, right? So this method is commonly used, the first one, trial dimension method, right? Now these are the steps. Now these are the required steps which we followed in our design. First of all, the first step, or step 1, we need to calculate the loads. Now I have discussed this in part 09 or part 08, I think so, part 08. Equivalent loading, that is trapezoidal loading or triangular loading, and similarly in part 10, I think so, I have already discussed how to calculate wall loading. So we have a plane of the figure of the building, and from that plane we assume different types of live loads. We calculate the building component loads by using their densities, and then finally we got the load in units of kilonewton per meter or kip per running feet. The second step is we find out the ultimate load, that is WU, by using the design combo or the design combination. We have various design combination, around about 9, right? So almost for a gravity loading condition or case, when we have no earthquake, wind, right? So in that case we have the governing equation is 1.2 dead load plus 1.6 live load. This is the governing equation. From this then we will determine the ultimate moment, that is WU for a singly supported beam case, WU L square divided by 8, right, for a singly supported beam. Then the next step is we will assume the width of the beam, assuming the width of the beam, that is B. Now this B is important, right? We have to assume such a width of the beam that it could not cause any kind of congestion of the reinforcement. Similarly, it can easily accommodate the bar, and it will not cause too much shear reinforcement, because the width of the beam also play a role in shear reinforcement, right? And width is almost assumed for a shallow beam, that is L by 15 to L by 12, right? So L by 15 to L by 20, sorry, L by 20. So for a shallow beam it is usually varies from L by 15 for smaller, this is for smaller or shallow beam, and this is for larger beams, L by 20. So after assuming the beam width, remember the beam width must be consistent with the column size or the wall size. This is the important step, right? That it can be easily accommodated over, let's say we have a beam right here, so the column size should be such that the beam side width should be such that it can be easily accommodated over the beam column size. After fixing the width of the beam, we will fix out the depth of the beam, which is one of the most important requirement. At the initial stage, we have to choose such a depth of the beam that it can pass the deflection criteria, shear criteria, torsion criteria, fire resisting criteria, and right, so these are the different criteria that we have to check the depth against those criteria. So that why we will choose the minimum depth, as we already derived an equation for it, mu divided by 0.205 fc prime into b. So this is from ductility criteria. When we want to ensure epsilon t should be greater than or equal to 0.005 and phi factor is 0.9. So if you want to ensure an under reinforced section, so the minimum depth will be this one. After this, we will find out the overall depth, that is d minimum plus 16 millimeter for a single layer of reinforcement, and d minimum plus 75 mm for a double layer reinforcement. This is for single layer and this is for double layer. So this will give us the overall depth. Now I have already discussed that when you are designing, when you are fixing the overall depth d, we have to consider those 7 requirements. I have discussed those 7 requirements, I think so, in lecture 02 part 10. So please go there and watch that lecture, that how to select this final depth. Now this is the we can say the end of the final the initial dimension. After this, we start to calculate the area of steel. So this is area of steel is step number 5. This is step number 5. So area of steel, this is important. To calculate the area of steel, we have 4 to 5 methods. The first method is direct solution. The second method is using design tables. The third method is using graphs, design graphs, and the fourth one is trial and error method. We know this method. And the fifth method is the approximate method, which we will not discuss this method, but we have approximate method. Trial and error method, I have recorded so many lectures. I have recorded lectures who were designed using graphs. I have recorded over the design tables, and I have recorded lecture over the design direct solution. But let me discuss these methods one by one. Right? On direct method, by using direct solution, area of steel can be directly calculated by direct solution. We know a well-known equation which I have derived in lecture 01 part 10. I have derived this equation, that is area of steel equals to 0.85 fc prime divided by fy into b into 1 minus square root b square minus mu divided by 0.3825 fc prime into b. This is a well-known equation, and it will give you the same result as given by the other methods. So this is the most easy method. we have another direct solution method in which we calculate the rho. So we already derived this omega times 1 minus under root 1 minus 2.614 divided by fc prime, this is r, right? And we will directly calculate rho from this equation, and then area of steel equals to rho times BD, right? So we already determined BD, so we calculate rho from this. We know this omega, which is also denoted by m, it equals to 0.85 fc prime divided by fy, and we know r is nothing, it is mu divided by BD square. So we will discuss this in part 09, the derivation of this equation. We have already discussed this, so please go there and watch this. This rho can also be determined by using another equation. I have already discussed this. Sometime we may use this rho. It can be because we already derived this equation, that is for rho, which is equals to 1 over m in terms of m, 1 minus square root of 1 minus 2 m r n divided by fy, right, where m equals to 0.85 fc prime divided by fy, sorry, this is 0.85 fy divided by fc prime, right? Here m is changed from omega, because omega equals to 0.85 fc prime divided by fy, I think so. This is omega, but here m is 0.85 fy divided by fc prime, and r in, which is also noted by r, which is equals to mu divided by pi bd square. So we will use this equation also sometime. This is also a direct method. We can use either this equation or either we can use this equation. And finally we find out the area of steel by using rho, that is steel ratio times BD. So this is all about a direct method. Now this here we have design tables. This is method 2, area of steel by using the design table. I have recorded lecture over this method as well. I will share the link. So when we are using design tables, so in design tables what we need to find out the mu divided by bd square value, right? Let's say this is x, and we need to choose this mu by bd square value. We choose that value in this table, in these tables, right? In these tables we will find out our desired value. Let's say this is mu by bd square is 1.8976. so this is our required rho value, right? And remember, this rho value is always fixed. It is derived on the basis of rho max and rho minimum. So that why then finally we will calculate rho times BD, right? So we will find out our area of steel. So what we need only need mu by BD square ratio. Similarly, this table is for 420, this is for 280, and this is for 300 MPa. And similarly, I have tables for 60K size steel and I have table for 40K size steel. This is 2.5, which is 17 MPa. This is 20 case MPa, 3 KSI, and this is 4 KSI, which is around about 28 or 30 MPa. So these are the design tables. I have calculated rho value, and I have already recorded lectures over this method. I will share the link and I will use this method in some examples so you can easily understand how to use this method. The next method is design graphs method. The design graph methods is simple. This is method number 3, using design graphs. So in design graphs, what we need, so you can see here in this graph, which is for 20 MPa roundabout, this is 3.5 K size steel. You can see this graph is drawn for mu, BD square and rho. So we will calculate mu by BD square, right? Mu, let's say it comes out to be it comes out to be 3. So by interpolating it, by just extending that point towards your desired steel, let's say the steel is 60 K size steel. So right, this is the point, and after getting this point, this is my point for 420 MPa. Now I will directly extend this point just below, like in this shape, and this is my desired steel ratio, right? This is rho, which is around about 0.005, and here you can see 0.01. so we will find out what is the value of this point, and that one will be my value, which is in between 0.005 to 0.01. So this is 0.005, so this value will be, this point is 0.006. Similarly, this point is 0.007. The next one is 0.008, and this one is 0.009, and this is 0.01. So the value is in between this is 0.008, and this is 0.009. So in between 0.008 and 0.009. So the we will use rho equals to 0.0085, right? So this one will be my rho value, and area of steel is calculated from this rho times BD, and we will find out the area of steel. So this is the way that we will use, by using this mu by BD and the desired grade of the steel, we will find out the rho value. And similarly, the next table is for 20 MPa. This is 3K size. This graph is for 3K size steel. So for 20 MPa we will use the same procedure. This is my third method, and the fourth method, which is well-known method, that is the ACI trial and error method. This is one of the conventional method, and we will use this method. Here we will assume the value of A. The A value can be assumed by d by 3 to d by 4. Most of the time we will assume A is equal to 0.2 times of the effective depth D, which we already calculated. After this we will use, this is trial 1. After finding the value of A, we will calculate the area of steel, that is area of steel equals to mu divided by 0.9 Fy into D minus A over 2. And then we will use the second trial. We will calculate the value of A, that is area of steel times Fy divided by 0.85 Fc prime into B, and we will check this A value, which we calculated right here with the assume value. If it close, we will stop the trials and we will calculate the final value of area of steel from that equation, mu divided by 0.9 Fy into d minus a over 2, and that one will be our desired value. If it not close, if this a is not close to that one, or this value of area of steel not close to this area of steel, let's say this is my area of steel 2, this is my area of steel 1. If area of steel 1 is close to area of steel 2, then that one will be our desired value. If not close, so we have to go for some other trials, 4 to 5 trials, and then we will got the final value. So this is all about trial and error method, and we have the last method, that is approximate method, that is method number 5, approximate method for area of steel determination. And we know for beams F, we calculate D, and that D is greater than or equal to mu divided by 0.205 Fc prime into B, then the area of steel will be directly calculated by using this equation, mu divided by 0.756 times D into Fy. This is approximate, right? And for beam FD greater than or equal to mu divided by 0.151 Fc prime into B, then the area of steel will be mu divided by 0.8 times Fy into D. So this will give us the approximate method. But remember, this is all about approximate method, remember, and we will not use this method for our examples. We will use the rest of the 4 methods. This is method number 5, and finally this is my step number 5. The area of calculation is my step number 5, right? This is area of steel calculation. The sixth step will be, we have to check the AS minimum, and AS minimum is 3 Fc prime under root divided by Fy should be greater than or equal to 200 divided by Fy, or in SI units this is 1.4 times Fy, right, for BW into D. It should be multiplied with, this should be multiplied with BW into D, right? And we will check whether our area of steel is greater than or less than, area of steel is less than, area of steel provided is greater than area of steel minimum and less than area of steel max, right? And finally, this is step number 7. This is step number 6 or 7, right? And last step is detailing. This is the most important step, right? This is the most important step where we have to make sure proper lapping, proper lapping of the bars, proper anchorage of the bars, proper cut-up points. So this is one of the most important step. And the step number 8 is proper sketching, proper drawings preparation. We will submit the structural drawings which should be checked properly, and the ninth step is bar bending schedule. So this ends up these steps. We will do all these steps in our design examples. You will see how we will do these steps, and how we follow these steps, and how we will design a beam.